Well, let's have another visit with the fundamental theorem of line integrals that puts the fun in vector calculus.
Fun? You call that fun? That was boring.
Aw.
You don't know how to have fun.
Well, yes,
You've been
I do.
acting really weird lately.
Well, no more than usual. But back to our problem here. The fundamental theorem of line integrals. If we have a conservative continuous vector valued function f, and then the integral f dr over curve C is independent of the path between any two fixed points in a region R. So what's called connected, a region is connected if any two points in the region can be joined by a piecewise smooth curve lying entirely in the interior of the region, and you can see why it won't work for the green one. If you put a point here and a point there, here a point, there a point, everywhere a point, you cannot connect them and stay in the region R. So this one's connected, this one isn't. So independence of path in conservative vector fields, theorem 15.6, okay? If f is continuous on an open connected region, then the line integral over curve C, f dot dr, is independent of path if and only if f is conservative. In other words, if f is conservative vector field, then this line integral is independent of how you get from one place to another. And if it's independent of how you get from one place to another, then the vector field must be conservative. And the last example we did with where both paths came up with the answer 896 thirds. I think that's the only time I've ever gotten that answer for any kind of a math problem. But that's showing the conservativeness. Okay, let's go with an example. For the force field f of x, y, z equals e to the x cosine y I minus e to the x sine y j plus 2k, we want to show the integral f dot dr over curve C is independent of the path you go from place to place with, and calculate the work done on an object moving it along from the point 0 pi over 2 1 to 1 pi 3. Well, the integral is independent of its path if it's conservative, and we can evaluate that by seeing what to ask you to recall. Conservative if the curl of f is 0. Well, the curl of f, here's our mnemonic device, there, I got it, for calculating the curl of f. And in our particular function here, it's this, right? So this is going to fill in down here for our m, and this will fill in for our n, and this will fill in for our p. And so, and if this is a zero vector, then we have a conservative vector field. I can't remember the theorem number, we had something like that earlier. So the curl of f, I times partial of y with respect to, partial of 2 with respect to y, which is 0, minus partial of negative e to the x times sine of y with respect to z, well, that's 0 also. And so then minus j times partial of 2 with respect to x, which is 0, and then minus partial of e to the x cosine y with respect to z. Well, that's 0 too. So we got 0i plus 0j. Let's see what the k brings. We've got k times partial of e to the negative e to the x sine of y. Oh golly, we got a number there. We got negative e to the x sine of y. Okay, what are we going to get when we go this route? The partial of this one with respect to y is going to be negative sine of x, but since we're subtracting it, it'll be positive e to the x sine of x. Notice that what we got is 0i plus 0j minus e to the x sine of y plus e to the x sine of y, so that's plus 0k, which is a 0 vector. Yay! It's conservative! So now that we know that it's conservative, we've got to find a potential function. Next video.